In a typical organic chemistry problem set or exam, they'll give you some type of reaction. In this case, we have, what is this molecule? We have 1, 2, 3, 4, 5 carbons. It is an alkene. It starts on the number 2 carbon if we start numbering from here. And the number 2 carbon also has a methyl group. So this is 2 methyl, 2-methyl pentene, usually naming it. We don't have to name it when we worry about mechanisms. But they'll give you a molecule like 2-methyl pentene. They'll draw it out like this. And they'll draw a reaction. They're saying in the presence of water and catalyzed by hydronium ions, we end up with this thing over here. And then they'll give you a bunch of white space below it. And they say, how did this happen? Give us the mechanism. And that's what we're going to do in this video. So let's start with this molecule right there, the 2-methyl pentene. So let me draw it right here. So we have double bond, carbon, I have a hydrogen, I have 2 carbons right over here, and then I have a carbon, H3C, and we put the H3 before the C just to make it clear that the carbon is what's bonded to the other carbon. That's why we don't write CH3, but that wouldn't be completely incorrect. And then you have H3C over here. And then we're going to have some hydronium molecules around. So let me draw a hydronium molecule. So it is an oxygen in the middle, and then we have 3 hydrogens, 1, 2, and 3. And oxygen also will have 1 unbonded pair of electrons. And it has a positive charge here. It has a positive charge. And the reason why it has a positive charge, if you think about just regular water looks like this. Regular water looks like that. 6 valence electrons. Let me do the valence electrons in another color. 1, 2, 3, 4, 5, and 6. The other half of these bonds comes from hydrogen's electrons. Now, in the case of hydronium molecule, in a hydronium molecule, you have a proton sitting out here. It has absolutely no electrons. And to form the bond, one of oxygen's unpaired valence electrons go to the hydrogen. And that's what forms the bond. So you can imagine that that electron is right over there. That's why it has a positive charge. Now, oxygen wants that electron back. It doesn't like having this positive charge. And we've seen in the last videos that sometimes the carbons, one of the carbons in the double bond, is pretty predisposed to, at least temporarily, giving up an electron. And we saw that the one that's most likely to give up an electron is the one that's bonded to the most carbons. And in this case, this guy right here is bonded to the most carbons. He's bonded to 2 carbons. This guy's only bonded to 1. He is a secondary, or if he loses his electron, it will be a secondary carbocation, as opposed to if this guy loses his electron, it will be a primary carbocation. This one will be more stable. So what we can do is we'll say, look, this electron that's at this end of this bond right here, it goes to the hydrogen. It goes to that hydrogen right over there. And then the electron that this hydrogen was taking from the oxygen will go back to the oxygen. And it all kind of happens simultaneously. This electron is attracted, I guess you could say, to the partial positive charge, because maybe this electron spends more time over there. And then this electron goes back to the oxygen to make water. So what happens after this end of the reaction, or this part of the reaction happens? So after that happens, we will, let me clear out this water actually. Let me clear out that little, that's not essential to our mechanism, to our reaction mechanism. So after that happens, what will everything look like? Well, we'll have our basic molecule. So we have a H3C, we have a carbon, we have another H3C. It is now a single bond. It is now a single bond to the other carbon, which is bonded to a hydrogen and 2 other carbons, CH2, CH3. Now this guy has lost his electron. That electron went to the hydrogen. So this guy now is a positive carbocation. carbocation by definition is positive. So maybe I'm being a little redundant there. So it's positive. And then this bond, let me do this in orange. This bond is now between this carbon and the hydrogen. The electron went to that hydrogen to form a bond. So this bond is now with this hydrogen over here, with this hydrogen over there. And then this thing that was a hydronium molecule will now be just water. So it will now be just water. So I'll draw it like this. It got its electron back. Let me draw its 2 electron pairs just like that. And then it has a hydrogen. It has 2 hydrogens. It is H2O. And you can imagine that maybe that was one of the electrons that was on the oxygen end. And then this was the electron that it had given essentially to the hydrogen, but it's now getting back. And now they're both back with the oxygen. That's the one that it always had on its end. And this is the one that it just got back from the hydrogen. Now, what do you think will happen next? Well, when you just look at the final products of this reaction, you say, well, at some point I have to have an OH attached right over here. And that's usually a good way to figure out what's going to happen next. So somehow it looks like this might attach to that positive charge. It was attached to a positive charge before. It was attracted to that hydrogen proton. So why can't it do it with the carbocation? And then once it does that, maybe we lose one of these hydrogens. And actually, this reaction, I shouldn't draw these strict arrows here, because every step of this reaction is really there's some form of equilibrium. It doesn't only go in one direction. Things can go in both directions here. So let me clear this. And let me show that these aren't just one-way reactions. They can go in both directions. But if we are trying to show a mechanism, we're assuming that we're going in the direction that we're, I guess, drawing this out in. So in the next step, let's make that oxygen attack that carbocation. Or another way, I guess a better way, the carbocation is attacking the oxygen. It's going to take back an electron. So let's do that. Let's draw it taking back an electron, or an electron being given back to this carbocation. So then we'll have, let's say, that orange electron right there. Let me do it in a different color. Say that magenta, let's say we have that orange one is attracted to the carbocation and forms a bond. Now what's going to happen? Well, now, let me draw it as an equilibrium reaction. Let me draw it in equilibrium, but we're going to go in this direction just to see how we can get that final end product. We have H3C. We have the carbon that was a carbocation. We have H3C. Now we have the single bond to a hydrogen to 2 carbons right over here. We have this business, that bond that was formed in the early part of our mechanism. Let me draw that. And then we have that blue hydrogen there that helps us keep track where things came from. And now this has attached. We have gotten that orange electron to the carbocation. It will form a bond. It's going to form a bond. And what's that bond going to look like? Let me draw this oxygen over here. So let me draw the oxygen like that. It has that electron pair still all to itself. It has the 2 hydrogens. It has the 2 hydrogens. It had that green electron. But now it's not just paired up with this orange electron. That orange electron it left the oxygen and went to that carbocation. So now the orange electron is right over there. And it formed this bond. Now carbon has 4 valence electrons. This carbon has 1, 2, 3, 4 valence electrons. This oxygen just lost an electron again. And so it now has a positive charge again. It now has a positive charge. Now, what do you think will happen next? We're very close to the final product. The thing we have here looks almost identical to the thing that we have to end up at, except we have a whole hydronium group, I guess we could say, or well, actually a whole water. We have H2O attached here. They only have an OH. And this this oxygen right here, it's positive charge, it wants to get one of its electrons back. It could take it back from here, or it could take it back from one of these hydrogens. And if it takes it back from one of these hydrogens, then we will be at our final end product. We will have a neutrally charged OH group right there. So how would that happen? Well, we are in an aqueous solution. There is water all around us. There are molecules of water. So let me draw one of those molecules of water. So let's say, let me draw one of those molecules of water that's just floating around. And maybe one of its electrons right here, let me color code it, that makes it a little bit more fun. Maybe one of its electrons are attracted to the partial positive end of this molecule, or this hydrogen. So I'll do it in green, it goes to this hydrogen. This hydrogen no longer needs this electron on this end of the bond, and so it goes back. It goes back to the oxygen. So it goes back to the oxygen. So it goes back to the oxygen like that. And then what is going to happen? What do we have left at that end? Or in general, now that we're after that part of the reaction happens. We have all of this stuff over here. Maybe I should just copy and, well, let me just redraw it. So we have H3C, a carbon single bond. We have, I'm going to draw everything in yellow that we started off with in yellow. CH2, CH3, H3C. And then we have that first hydrogen that got attached on this end. We figured out it was going to be this end more likely because of Markovnikov's rule. One way to remember is this carbocation was more stable. The other way is the side that has more hydrogens will get more hydrogens. The side that has more functional groups will get more functional groups. But now we have all of this business. We have this magenta bond here, and we have an oxygen. We have an oxygen in the middle. It is still bonded to that hydrogen over there. Is still bonded to that hydrogen over there. This pair of electrons, I'm just going to do it on this side just so we can draw it how we conventionally draw it. And now we had, and let me make it very clear with the colors. We had this electron on one end of a bond, so it's still there on that end of the bond. And then we have this electron that was with the hydrogen, but now it's gone back to the oxygen. So now it's gone back to the oxygen. So now we have two pairs again. We have 6 valence electrons around the oxygen. 1, 2, 3, 4, 5, 6. It is neutral. And now one of those water molecules has become a hydronium molecule. So now that water molecule looks like this. The thing that was a water molecule looks like this. It has its lone pair, and then it has one end. That's that electron right there. But this blue electron went and joined the hydrogen. So it has that blue electron. It has that blue electron that went and joined the hydrogen. Let me draw it a little closer to the hydrogen. Right there. And then it has that bond. It has the bond. So when all is said and done, we were able to get to the molecule that the mechanism or that the reaction described. And it was actually the most reasonable path to follow. We followed Markovnikov's rule. We figured out that this was the most stable carbocation. And then we just added the water. This is an addition reaction of water in the presence of an acid, in the presence of hydronium. Hopefully you found that vaguely useful.